In the last video, we introduced the alternating series test, which is a way of testing whether a series whose terms alternate between positive and negative, whether that series is going to converge or not. And the test component is actually the first observation, and that is that all that we need to do to check if an alternating series converges is make sure that the individual terms are going to zero. If indeed that is the case, then you can conclude that the alternating series converges. And secondly, we showed that when you look at the partial sums, they're going to keep bouncing back and forth. They're going to keep being larger than smaller than larger than smaller than larger than smaller than the true value. And not only that, if you take any partial sum, you can actually estimate how close it is to the true sum by looking at the next term. Okay? All right, so let's actually apply that to an example. Let's look at the series whose terms are negative 1 to the n plus 1 over root m. So S looks like, well, we plug in 1, we'll have 1 over root 1. Next, we'll have negative 1 over root 2 plus 1 over root 3 minus 1 over root 4, and so on. And the question is, what is this converging to? At least we'd like to estimate within 0.1. Now, before we go into estimating it, it would make sense to actually check to see that it does indeed converge. And so all we need to do is look at the limit as n goes to infinity of the individual terms. Their absolute value, that is. And notice if you take the absolute value of the numerator, we'll just get 1. And the denominator is already positive, so we don't need that. And clearly, the denominator is growing, the numerator is not, and so the terms go to 0. And so since the series alternates and the terms go to 0, it converges by the alternating series test. Okay, so it does converge. Alternating series test tells us as much. Now, we can also ask ourselves the question, does it converge conditionally or absolutely? All right, so we sort of answered converges. Does it converge? And now we'd like to determine, does it converge conditionally or absolutely? And ultimately, we'll get to the main question in just a moment. And to do that, we need to know, does it converge both with absolute values and without? Or does it only converge when we have this alternating behavior? And so what we need to do is look at the series where you make all the terms positive, which would be 1 over root n. And notice that is just a p-series with p equals 1/2. And so if you remember our p-series test, that is less than or equal to 1. So this diverges. And that means that the series converges when it alternates, but it doesn't converge when you make the terms positive. And so we would say that the sum of negative 1 to the n plus 1 does not converge absolutely. It only converges with the alternating property. So it converges conditionally. All right, so now on to the main question. If S is exactly what this sum is, how do we estimate S to within 0.1? Now, rather than answering that question right off the bat, let's start looking at some of the partial sums to get an idea of what's going on. Okay, and again, I will go back to Desmos to help with that. All right, so our series is 1 over the square root of n. And so you'll notice the first partial sum is 1. The next partial sum, it looks like, is around 0.293. And what that suggests is that the true value must lie somewhere in between those values. The 1 is too big, the 0.293 is too small. And if we're not satisfied with that estimate, since that's a pretty wide range, that gives us a range of 0.7, we can't be very confident that our either of those estimates would be correct. We can just go one term further. The third partial sum would be, well, I'm going to add 1 over root 3 to that, which is around 0.87. And so notice now we've narrowed it down. Now we know that the solution's between 0.93 and 0.87. And we could continue this process. Maybe that's not a narrow enough range for us, so we'll go to the next term. And so now we know it's between 0.37 and 0.87. And we could go as long as we need to. And by the way, this log 2, that green line, is not actually the answer, so let me get rid of that. It's a little bit misleading. This converges to something else. Okay? All right. Now notice, if I go all the way out to the 20th partial sum, now I'm down to S19 is 0.718, and S20 is equal to 0.494. Well, those are still relatively far apart, right? There's still a gap of over 0.2. So we can't be entirely confident that we're close to the answer, knowing that the sum is in between those two values, right? We wanted to be within 0.1. This is not far enough in the series for us to guarantee that. And so although this process of just comparing consecutive partial sums can in principle get us to the answer, in practice it might be nice to know how far do I need to go? How many terms in the series are required to get a good enough estimate? And we can actually determine that exactly, or at least we can determine with confidence if we've gone far enough by recognizing that the difference between our two terms is just the last term that we added. Okay? So let me go back to our notepad here. All right. So if you take the n plus first partial sum, which is a1 plus a2 plus all the way out to an and an plus 1, and you take the nth partial sum, which is a1 plus a2 all the way out to an, well, if you subtract them, notice, well, the a1s will cancel, the a2s will cancel, the a3s will cancel, the ans will cancel, and we'll be left with just an plus 1. Agreed? And so in particular, the width of that interval is equal to the absolute value of that last term. Okay? So if we want to know that we want a range to be less than 0.1, we can say, another way of saying this is that this gap between the n plus first partial sum and the nth partial sum, well, that's definitely bigger than the gap between the true sum and the nth partial sum. Right? Since we know that when I add that next term, I'm going to overshoot. And so if I want my estimate Sn to be within .1, then all I need to do is ensure that the next term I'm about to add is less than 0.1. So we'll say that one more time. We recognize that when we keep adding more terms, the partial sums are always going to straddle the true value. So one's going to be too big, one's going to be too small. And what that means is that their difference is bigger than the difference between either of those partial sums and the true value. And so that's this piece right here. And so we can be very confident that if 0.1 is bigger than the next term, well, and the next term is bigger than their error, then our error in our estimate, Sn, is less than 0.1. Okay? So let's see if we can apply that to answer the question. How far do we need to go? Remember, we're interested in the series where an was equal to -1 to the n plus 1 all over n over root n. So we want that to have an absolute value that's less than 0.1. And in this case, we're interested in an plus 1. So that would be -1 to the n plus 1 plus 1 all over root n plus 1. Okay? So if we go out far enough in our sequence, so that next term is smaller than 0.1, we'll know we've gone far enough. And so let's simplify that a little bit. Notice the numerator is just -1 raised to a power. So that's just 1. And the denominator is a square root, which is positive. So the absolute value doesn't do anything to that. And so we can simplify that to 1 over root n plus 1 is less than 0.1. And if we were to, well, let's write that 0.1 is 1/10. If we were to multiply both sides by 10 and multiply both sides by the square root, we could say that that'll turn into 10 is less than the root of n plus 1. And we're getting closer. What we ultimately want to know is how big does n have to be? And so let's try to get n by itself. If we square both sides, we'll have 100 is less than n plus 1, or 99 is less than n. Okay? So there's a whole bunch of algebra. Let's put these pieces together. If n is greater than 99, then what that tells us is, working backwards, the absolute value of an plus 1 is less than 0.1. And that means that the true sum minus Sn is also less than 0.1. And so if we estimate, if we use the approximation, Sn to estimate S, our estimate, will be close. And by close, I mean within 0.1 of the true answer. All right, so that's good news. All we need to do to get an estimate within 0.1 is to use some partial sum with n greater than 99, and n equals 100 seems like a good choice there. All right, so we'll go back to our calculator, and we will plug in 100. And it says, notice the term we were about to add was -0.1, and Sn is 0.555. So S100 is around 0.555, and the true value that must therefore be pretty close to that. And if we add a few more terms, you'll see that we're going to be pretty close to the true value. The true value is actually something closer to 0.599, and in fact, maybe it's 0.6. I'm not sure exactly what the exact answer is, but that seems like a plausible guess based on what we've seen thus far. All right, so big picture, what do we do here? We started with an alternating series. We showed that it converged by showing that the individual terms go to 0, and that's all it takes with alternating series. It's much easier than checking for convergence for a non-alternating series. All you have to do is take a limit, show that you get 0. Now keep in mind, that only works for alternating series. Say it with me. That only works for alternating series. For series that don't alternate, the terms going to 0 tells you nothing. But for an alternating series, it is enough. Okay, so that was the first thing. Next, we checked for absolute convergence by looking to see what would happen if we just made all of the terms positive. And in this case, we saw that we had a p-series and it did not converge when the terms were positive, and so we concluded that we had conditional convergence. And then lastly, we wanted to estimate our series to within a particular threshold, 0.1. And we did that by basically figuring out when do I first add a term that's 0.1 or smaller. As soon as I'm starting to add things that are 0.1 or smaller, I know that my sum is not going to change, my estimate is not going to change much anymore, and so that's going to be a good enough estimate at that point. And so it just took a little bit of algebra to figure out when the terms get smaller than 0.1, but once we did that, we were able to get very good estimates for the true value. Okay? All right, we'll do another example of this in the next video.